is CORDIScovery. Hello, welcome to this episode of CORDIScovery with me, Abigail Acton. Today we are looking at 3 novel ways to cut back the waste we produce by repairing, reusing and recycling. Did you know that it takes 3 to 4 tons of nitrogen-rich substrate to grow a ton of mushrooms? There's a lot of it. Over 3.5 million tons are generated in Europe every year. What happens to that once the last mushroom's been picked? Recycling is a key battleground in combating climate change, but how can we sort through everything to reclaim what can be reused? Currently, metals like aluminium, gold, silver and zinc can't be economically recovered from mixed recycling. Most recyclers do not have a sustainable solution for the separation and recovery of these valuable resources. So how can that change? And then there's industrial plastic. In Europe, 1.9 billion items like plastic crates and pallets are used by transport companies, and there are more than 20 billion plastic bins used on our city streets. When any of these break, they're thrown away. Billions of wasted items every year. What if they could be repaired cheaply and effectively and then be reused? Our 3 guests, whose work has been supported by the European Union's Horizon 2020 programme, are doing their part to come up with innovative solutions. Gent is the managing director of Recresco, a UK glass recycling company that is using X-ray fluorescence, shape recognition and machine learning to make recycling more efficient. Tim's interest is in how to make the circular economy more of a reality. Welcome, Tim.
Hello, everybody.
The commercial managing director of the Spanish company Plastic Repair Systems, Alfredo Neila, has set out to make repairing industrial plastic objects such as crates and pallets more financially viable than throwing them away. Hello, Alfredo.
Hello, good morning.
Pablo Martinez is one of the brains behind Smart Mushroom, which has come up with a new way of treating the waste produced by the mushroom growing sector, transforming it from the environmentally challenging byproduct to a valuable resource. Pablo, welcome.
Hello, everybody.
Hi, let's get to it. Tim, I'm going to start with you. One of the biggest problems recycling processes face is sorting the mingled materials so that the reclaimed final product is pure. The OMR project is putting in place advanced technologies to help make the whole process more efficient. So, Tim, how did you get involved in the idea of extracting non-ferrous metal from glass waste?
We, as a glass processor, we process about 20% of all the glass bottles in the UK for recycling back into glass bottles, which is a really good system that's evolved over many years. Throughout those years, we've had a byproduct from that we called aluminium tops that we screw on the top of the lid. We also have aluminium closures that get mixed in. There are also other metals in there, which are a contamination to that aluminium. If we want that aluminium to be reused, we have to clean it to within an inch of its life. So it's as good as raw material. Mm-hmm. And that's the challenge. And that interested me because it's a very valuable product and it's a challenge to get it clean enough to reuse.
Right. So prior to your work on this project, when you were first sort of beginning to realise that there was a resource there that was just not being harnessed effectively, what was happening to all the aluminium?
The aluminium, a lot of it was going to landfill because it wasn't economically viable to recycle. In the last few years, it's been going into aluminium smelting furnaces, just as a weighbridge ticket. But actually, when it gets in the furnace, because it's so thin, it disappears into smoke and ash up the chimney. So we are kidding ourselves if we think that's being recycled. It isn't. It's a contamination and a pollutant at that point.
Right. Okay, great. So there was clearly a problem that needed to be addressed. So can you tell me a little bit about the techniques that you were using already in the glass sorting and how then you adapted and reformulated those ideas to apply to metal extraction?
So to make sure our glass is clean enough, we have to use an X-ray fluorescence system, which analyzes the molecular structure of the glass to make sure that it isn't lead crystal or zirconium-based glass, which is heat-treated. Neither of those are good in the furnace. One doesn't melt, and one puts too much lead into the container, which is for human consumption. That machine, we found, could also differentiate between different non-ferrous metals. So we were able to separate the aluminium from zinc, lead, copper, brass that was also present in that waste stream. We can't separate that material by hand in Europe. It's too expensive. So the material ends up being, as I said earlier, sent to landfill or sent to China, India, hugely valuable resource being wasted. If you can make that happen using technology, then you're onto a winner. Because technology, whilst it's very expensive, it runs 24 hours, 7 days a week. and it's repeatable, and you can guarantee the end product, the quality of the end product. It's absolutely essential for our business to guarantee the quality of the end product. You can only do that with technology.
Right. So, I mean, once you've invested and put it in place, then it takes care of itself, as it were, apart from maintenance. But so that's the X-ray technology that we're using. But I think you were using other really quite cutting edge means of sourcing and also at great speed. Tell me a little bit more about the actual process and how it unfolds in your plant.
Okay, so the glass comes into us, it's in very poor condition, hugely contaminated with paper and other non-glass items. Our plant covers 2 acres.
Wow.
So we put it in a hopper at the beginning, and it goes through grading, which is really just mechanical. We then use magnets for ferrous, eddy current separator for the non-ferrous. We have camera technology, X-ray technology, and laser technology.
What was that separator you just mentioned after the magnetic separator? You said eddy current, I think. What does that mean?
Yes, the eddy current separator. So that is a drum that's 1.5 meters long, weighs about 1/3 of a ton.
Wow.
And it spins at 3,000 revs per minute. And it generates an electronic field around non-ferrous metal.
Okay. And then what happens to it?
It is repelled. So it literally jumps into the air.
Ah, fascinating.
Of a conveyor belt.
Right.
And as the material passes over, it has no effect whatsoever on the glass because it's not a metal.
Mm.
In non-ferrous metal, brass, copper, all of those metals has the same, it's an electronic reaction.
Right.
And it repels it and it jumps off of the belt onto a neighbouring belt.
Fantastic.
And then we go and put it into a bay. It's a remarkable thing to see. It's like magic. It isn't, obviously.
So it's almost like it's sort of leaping out of the container and volunteering itself.
Yeah, it's quite funny because obviously it's quite high value material and it's jumping out of the conveyor belt and throwing itself
at you. Yeah.
So yeah, it seems a waste not to do something more exciting with it than put it to landfill, you know?
Yeah, absolutely. So then that goes down a process through this large plant that you were mentioning. You said, I also believe that you're using machine learning and shape recognition, no?
Yes, and that's because some of the contamination in the aluminium lids with the tops is coated with copper. It's actually zinc, but it's coated with copper or chrome. And sometimes it looks like brass, like a door handle, but it isn't. It's zinc underneath, and you can't put that in the brass because it looks like brass.
Right.
You have to know what that is. So even if you did have people trying to sort that material, they would think that it was brass. The machine, however, knows that it is not.
And how does it know that?
It knows that because it can analyze the surface, and if the surface coating is too deep, then it can look at the shape. So if we find a contaminant, a piece of zinc in the copper bin, then we show that to the machine and say, next time you see this, we don't want it.
Fantastic.
And that takes a while because, but everything is repeated in recycling. Everything, there isn't a one-off. There isn't, oh, well, we've never seen this particular door handle before. That doesn't happen. So once you've got that data bank of material and objects, you can then fire on them simply because of their shape recognition.
Excellent, fantastic. And does the machine also, is that also the place where it would be able to identify that even though something looked like brass, it wasn't brass, or is that a further step in the process?
No, it has to be a combination of the two. So you can say, look, this looks like a brass coin, but in actual reality it isn't. This is ink washer.
Right. And but the shape would be the same. So the shape learning, the machine recognizes, okay, find this shape now. You want me to do this with that because you've programmed me and you've told me that's what you want. But how can it tell what the material actually is?
It's doing that by the X-ray. So you've got X-ray and shape recognition, and they work together. That combination tells you what it actually is.
Well, that's absolutely fantastic. It sounds a marvelously high-tech approach. And I don't know, I mean, many of us have thought in the past of recycling as being perhaps quite manual and not necessarily quite so cutting edge. So this is very interesting. But it must have taken a lot of trial and error before you refined your approach. So you're talking about a high degree of precision. How long has it taken you to get to the point where you can be as precise as you're describing?
This project so far has taken 3 years.
Right. And prior to that, what was this building on?
This is building on the experience that we've generated within the glass processing plant. It's very much the same technology, but just slightly different use. And that's been 20, 30 years in the building.
Right. So indeed. So this is a long evolution. And I suppose, obviously, it must be the case that there's new technologies coming online that are helping you.
Why I love this business is the new technologies. We help develop it. We tell people what we need. We use crossover technology. We introduce it in our plant and we make it work by sheer determination.
And passion. Absolutely. Excellent. Okay. And the impact of all this hard work now, do you have some idea, Tim? Can you tell us some statistics, for example? Do you have any idea of how much you're managing to save from landfill than wasn't being saved before? Any idea of the quantity of change that you're making here?
Surprisingly enough, if you take the aluminium lids alone on the bottle, in the UK, we produce over 100 tonnes per week from our recycling operations across the industry.
Right. And then that goes back into being used as quality aluminium.
All of that goes back into a food grade application, but it's a recycled content now, so it ticks an awful lot of boxes. Interestingly, though, this technology can then be used to sort other streams of mixed non-ferrous metals, which traditionally have all gone to China.
Okay, great. So we're not exporting our problem, and we're also keeping within our own value chains a valuable resource. So yeah, win-win.
Exactly. The driver to this, Abigail, is resources. This is getting very, very political, especially this year. These resources, most resources that we need in this country, come from organisations and countries that may not particularly like us. And not only are we buying these resources off of them, in some cases, when we finish them, we're giving them back.
Right.
It's absolute insanity. We have to stop doing that.
So it's almost as if we're just renting them, as it were. Yeah. Super. Okay. And where to next for Recresco then?
So once we've completed the plant and we've proved its concept, this is repeatable. This is a Europe-wide problem. This can be repeated right across Europe. There are hundreds of thousands of tons each year of mixed non-ferrous metals that are being sent to China and India for reuse over there. We should be sorting this here in Europe and using it in Europe.
Fantastic. Okay. And we seem to be focusing on bottles and tops and things like that. But the aluminium itself, where will that end up, do you think? The
aluminium content of packaging has to have a recycled content, and that's where it will go. The consumer is driving this and demanding a higher recycled content in packaging. So this will be returned to packaging, so the recycled content is higher.
Okay, that's great. So that's the aluminium and other metals returning back potentially to the industries that were initially using them, but could they perhaps be destined for completely unrelated industries?
Yeah, all manufacturing requires a recycled content nowadays. So we're now seeing recycled materials have a premium value over and above raw materials, simply so that the claim can be made that our vehicle, our aeroplane, our toys, they all have this value because of the recycled content within them.
Right. So it's a very strong selling point to say, yes, indeed. I mean, you see it also in the computer sector. Yeah. One more question for you, Tim. If there was one industry barrier to the successful uptake of the product that is coming out of your recycling plants, what is it? What is the one bottleneck when it comes to actually trying to get your material back into the system?
I think people have to accept that the recycled content costs a lot to get it to the quality they require. And we need to see the value, the true value of the recycled content. It should be premium. It is in places, but it's not enough. There isn't a shortage of recycled material. There's just a lack of value. If you pay the true value so that you're covering the cost of the recovery, then this material will all be recovered. The only reason it goes to China is because it's the cheapest route. So we need to recognise the value that the recycling industry adds to this material.
Fantastic. Thank you very much, Tim. That's interesting and also very clear and surprisingly cutting edge. I thought that was absolutely fascinating. Thank you. Alfredo, I'm going to turn to you now. The PRS project has developed an innovative way to repair industrial plastic items, restoring their former quality and strength and keeping them out of landfill and incinerators. So can you tell us a little bit more about the problem, Alfredo? What were you trying to change?
Yeah, well, what we have detected is that in Europe, there are about 1.9 billion plastic boxes, pallets, generally called RTPs, returnable transfer packaging. They are used all over the industries, like you name it, the automotive, food industry, pooling. And we saw that 10 to 15% of this huge park, was being damaged. And when damaged, there was basically two options. One was throwing them away as fill land. And the second option, which is a good option, circular economy, is recycling. Now, when you recycle these elements, there are two issues. One is that you have 3.73 kilos of CO2 emissions per kilo of plastic recycled. which is considerable.
Yes, indeed.
The second one is the economic part, like when you have to grind, recycle the plastic and then inject it again, that's a significant cost. So the value proposal of plastic repair systems have two main pillars. So one is the sustainable pillar. So instead of 3.73 kilos of CO2 emissions, we have 12 grams
wow.
of CO2 emissions.
That's a huge difference, Alfredo.
Huge difference. So if you consider this amount, we're talking about 410,000 million tons of plastic every year, and you translate this into CO2 emissions, we're talking the billions too. So the scope is just huge.
Right.
So what we have done is we have developed our own technology, and we have been able to manage the great variety of this breakage. So at the end, we don't have such a standard product. So each breakage is different. And we see that the main issue to have a business case here was to handle this variation, right? So that's why we are, in business. The technology, the basic technology was there, but we kind of have applied new technologies to kind of solve this issue.
Okay, so basically, obviously, things are broken in different ways, and each type of break requires a different way of repairing by the nature of it.
Yes.
That must present a vast diversity of problems to solve. So, for example, if something is snapped slightly or if something is worn through because of too much friction, it's a completely different mechanical problem for the solution, I would imagine. So tell me a little bit more about the system that can actually interpret what this object needs in order to be repaired.
This is very much like what Tim was mentioning. We are also relying heavily in the new technologies and artificial vision and machine learning. So basically what we do is we have we go step by step. We have, first of all, we have like a family of components and a family of breakage. So we start feeding data to the machine. And the more data we feed the machine, the more the machine or the algorithm is able to detect and to classify different types of breakage. And with different types of breakage, we have different processes. So that's the key thing. That's the base. And then in parallel, we are kind of going deep with each technology. We have our own thermal welding technology. We produce our own material. We go in automation also for some other types of breakage. We have several patents with several machines. So that's our scope, right? To kind of go, first of all, to handle the variation. And once we have that classified, go through an industrial process so we can make a viable economically dispensable repair system. Okay.
And do you find that there are many objects that you get that you just can't repair because your machines can't interpret what the problem is, or is it the case that 100% of the broken items that come to you are repaired? How does that work?
No, actually what we do is when we classify, we put aside the plastic that is, let's say, really damaged and is a borderline with economic viability. And what we do is we have them as donors. So what we do sometimes is when there's big damages, we cannibalize these very damaged components. We take parts of it and we kind of transplant them to a receptor, to another component. So those are the cases where we can somehow manage the very damaged and save somehow more of the not that severely damaged components. So long story short, we have about 80 to 90% recovery rate average. Yeah.
Well, that sounds very significant. And what happens? So industry comes to you with a collection of a stockpile of broken objects and asks you to repair, or do you buy those broken objects from an industrial source and sell back? How does that work?
Well, no, not at all. It doesn't work like that. I wish it could work like they would come to us. So this
is if only was so simple, huh?
This is a hidden waste. So this is something that they don't see as a waste. So they recycle. They think, we're in a circular economy process, but they don't see that this can be enhanced and improved. In some cases, there are a percentage that it's not viable to repair, so you have to recycle anyway. So that's still an option, but the vast majority you can repair. So what we have to do is, first of all, raise awareness of how things can be done. And actually, it is surprising how so many big companies that are so much into sustainability, they don't know about this. And even when they know, it takes quite a bit time to kind of go through their, let's say, decision-making process to go ahead with this, right? But once they see it, it goes very fast. So right now we're scaling really, really fast because everybody or the main customer base that we're facing, they're buying it and they're going for it.
Yeah, because once they've tried it and see how it works, then they're into it. Yes, I get that. Okay.
Absolutely.
Yeah, super. And so where to next for your company? What are you actually doing right now? You say you're scaling up.
Yeah.
How's that going?
Well, right now I'm talking from Mexico. We are going here, also growing very fast in Mexico. The government regulatory system or the regulatory frame is not that focused on sustainability, but since Mexico is exporting 80% of all its production to the US, and the US is tracking all the carbon footprint in the supply chain, I mean, all companies exporting to the US are forced to kind of like go with this. So we have a very good reception of this concept. We have an aggressive, commercial-wise, we are going to scale up the business in Europe and the Americas for the next 2 to 3 years. We're going to open about 10 to 13 new plants.
Wow, that's quite a lot.
Yeah, that tells you a little bit what's the reception of this idea. And in terms of product development, what we're doing, we're going to, let's say, cheaper, simpler systems that are economically speaking very difficult to repair, but we are kind of like automating in the industrial processes, and we are able to do some of them. So we're expanding our portfolio of systems that we can recover.
So when you say systems, you mean items?
Yeah,
right.
Yeah, indeed. Packaging systems, packaging items, yeah, correct.
Okay, so you're broadening the scope of what you can actually take on.
Yeah, indeed. So we're going deeper. Right now, we have let's say the big items, crates, pallets, and so on. They're like quite heavy, about 30 kilos, 60 pounds and up. And right now we're going with items that are a few kilos. So that's also giving us a huge projection and ability to grow. Yeah.
Right. But it must be quite a technical headache as well, because if you've been repairing items that are very big and now you're going towards things that are much smaller, then presumably you need to think again about how everything is scaled up. But anyway, it sounds fascinating. Does anyone have any questions for Alfredo? Yes, Tim.
Alfredo, do you find that your product gets the respect it should do, being as it's recovered and recycled? I noticed earlier you did mention that trying to get people to buy your products instead of brand new ones. And is it getting easier to sell your items because they are recovered?
Yeah, actually, yes, that's an issue at the beginning, but we went through this process already. So we have a very big customer. I don't know if I can say the name here, but this is the biggest pooling company in the world. We have solved a lot of problems for them, and we have a very strong, let's say, reference there. So at the beginning, indeed, it was extremely difficult to do this because there are items that are security-wise very critical. I mean, if you pile these items in towers of 6-8 meters, something goes wrong, they fall, they can kill the person. So this is a very critical thing. But we have a certified method. We have all possible certifications, you name it, ISO, IMPLUS, federal authorities in the US. And yeah, that's actually a competitive advantage to us. It's a barrier, let's say. We do this well, we can prove it. And it's not that an easy thing to do. That's a very good question. Thank you, Tim.
Thanks, Tim. Yes, that's a good point. Okay, well, thank you very much. I'm going to turn to Pablo now. So we've been thinking about glass and metal, and we've been thinking about plastics. Pablo, now we're going to think about organic waste with you, because your project, Smart Mushroom, is dealing with a problem that I suspect most of us haven't even thought of when we're tucking into our mushroom omelette. And that's what happens to all the growing material once the last mushroom is harvested. So tell us more about the problem. Where do mushrooms come from, and what is left behind?
Okay, first, I would like to remark that mushroom cultivation is a circular sector in itself because it uses residues and byproducts from agriculture, like cereal straw, and livestock, like chicken or horse manure, as a source of nutrients to elaborate the substrate for cultivate the mushrooms. But yes, mushroom cultivation generates also residues. From each kilogram of mushrooms produced, there are generated 3.3 kilograms of spent mushroom substrate.
Wow. Okay.
Which means 3.70 million tons annually in Europe. So this is a very large amount that has to be managed.
Indeed. Why can't we just take it back out and put it straight back on fields?
As you have said before, it could be used in agriculture by adding it to the soils as fertilizer. However, nitrates directive set a disposal limit that makes that large quantities of spent mushroom substrate cannot be simply spread in soils next to mushroom growers' facilities, as there is a high risk of water pollutions or leaches by nitrogen.
Oh, I see. So that's the problem with just trying to spread it around on the soil. Okay. So you see a large quantity of this waste product which just can't be put back outside and spread around because it's very nitrogen rich. So what caused you to see this problem and to feel that you wanted to try and find a solution?
Okay, so I'm absolutely convinced that it's necessary finding solutions to manage waste generated by humans, of course, while reducing the generated waste, to avoid the negative impacts on the environment. This topic is related to my personal interest, as I love the countryside and nature, and these spaces needs to be preserved.
Okay.
Of course, I also think that it's essential to demonstrate that recycling technologies can bring an economic benefit to the sectors that are generating this underexploited waste, because from my point of view, profitability is going to be the key aspect to promote the circular economy and increase the positive reaction of many stakeholders.
Yes, just exactly what Tim was saying. Yes, indeed. So what was the solution that Smart Mushroom has come up with to deal with this problem then?
The aim of the project was to develop an organic pelletized fertilizer. But to perform this activity, the spent mushroom substrate must have less than 20% moisture content. So we were looking for a profitable and environmentally sustainable process to reduce the humidity of the material. So the process instead has two different phases. First, spent mushroom substrate is used as raw material to produce biogas into an anaerobic digesters. And after this stage, the biogas produced is used as a source of energy into a dryer for heating. So we use this heating to dry the spent mushroom substrate. After this stage, this material can be pelletized.
And when it's pelletized, what's it used for?
When it's pelletized, it's used for agriculture because it has a very good market value. And it can also be mixed or blend with other nutrients prior to be pelletized. So it can be done like tailor-made fertilizers.
Okay.
So this is a very important point to develop specific products for different crops.
Right, excellent. So basically, you're taking the actual problem itself, using that to create biogas, which then makes heat, and then you're desiccating the rest that's left, and then it's able to be reused as fertilizer. I think that's absolutely fascinating. How long did it take you to come up with this solution?
Well, this solution, it was like a preparing time of 1 year prior to build the proposal, and then the project was 2.5 years.
And how does the mushroom substrate come to you, and how does the fertilizer leave you? In other words, do mushroom companies come to you with great big trucks full of the stuff, and then what, do you sell the fertilizer? How does that actually work?
In La Rioja region, where we are located, this region produces the 45% of Spanish mushrooms. So there's a dedicated waste management plant where all the growers bring the spent mushroom substrate. It's transported in trucks and bring it into this facility. So for us, it was, this logistic is done. So it's more or less easy just to manage and pellet to process all this material and be able to pelletize them.
Right. And then do you sell it or how does that work?
Yeah.
And does the cost of the selling, I mean, the price that you get from it, does that cover the cost of actually running the desiccator and all your processes? In other words, do you break even?
Actually, we are selling the pellets for these fertilizing applications. And the process is profitable. We are earning money from this. There's an economic profit from this process, but it is just because we use the biogas for drying. Because if you use an external source of power to dry the material, it's not going to make sense. It's not going to make any profits.
No, but that's part of the sweetness of your solution, is that it's sort of completely circular.
Yeah.
You're using the problem itself to solve the problem.
Yeah.
So it's a very neat solution. That's fascinating. And where to next for your company? So this is a pilot plant. Are you now going to build a bigger one or elsewhere, or how's that going to work?
Okay, right now we have installed the pilot plant in the Smart Mushroom project, and the pilot plant is running. We are pelletizing the spent mushroom substrate, and right now the pilot plant can process up to 3,600 tons per year.
Fantastic.
And all of you can see videos of the pilot plant working in the project website. And the next steps will be increase the commercialization for the technology. As it was planned, of course, just to commercialize the technology, but the COVID-19 has impacted so much the demonstration activities.
Of course, it's impacted everything.
Yeah. So right now we are involved in the demonstration sessions. So anyone can visit our facilities and see how it's working. And yeah, we are quite happy because there is interest from mushroom sector, not only from European companies. We have also been contacted from companies from the United States, Canada, and Australia. So yeah,
super.
We are trying to increase the commercialization of the technology.
Super. So for your business as well, it looks like things are moving in the right direction. That's excellent. Thank you. Does anyone have any questions for Pablo? Yes, Tim. Thank you.
Hi, Pablo. Listening to what you were saying, I was quite interested that the solution in the past has been to put this product on land, and that, I guess, is a pollutant then, and pollutes the surrounding streams or possibly surrounding farmland, and that your solution obviously fixes that. Do you think that the industry is really pleased about that, or is that a cheaper option that they've been getting away with that now they'll have to stop doing?
That's a very good question. Right now, the industry is very interesting because if they don't recycle this material, they have to pay a fee for landfill. So yeah, of course they're interested because then they can get a profit from a material that in other way generate a cost. So yeah. In some years ago, it can be disposed in landfill in the areas surrounding the mushroom production facilities. But right now, it has to be managed in a waste management facility. So yeah, they're interested in the technology because of this profitable approach.
Excellent. Well, that sounds wonderful. Thanks, Tim. Any other questions for Pablo? Yes, Alfredo.
Yes, I have a question, Pablo. It's a really interesting project. It's amazing what you can do with that. And I was caught by the fact that you were being approached by companies from Europe, US, and Canada. Is there any regulatory issues? Is there like a limit to your market in other countries because the regulations are not that strict and therefore it might not be as economically viable?
There's no real limitations for the transferability of the technology to other countries because this can be installed in any places that where mushroom cultivation is going on. So no, right now there's no limitations for the regulation of different countries. They are all open to include these technologies.
Even if there's no fee to throw the SMS, it's still more economically interesting to sell it somehow.
Yeah, because if a company can just throw them the material, the spent mushroom substrate, they are not earning anything. It's €0 or dollars. It's okay, but by applying this technology, they can get some profit from the waste valorization. So
nothing like profit as a motivator, huh?
Yeah.
Does anyone have another question? Yes, Tim.
Similar lines to Alfredo there. I think you're talking to a panel of entrepreneurs, and I was listening to Pablo and looking for the ka-ching moment. And
good term.
When he mentioned that you're not allowed to spread this substrata on the land anymore, our industry was pushed by legislation, and we were really up against it until legislation stepped in and said you can't send this this to landfill. It's got to be recycled. Pablo is there. They've got a relatively cheap outlet on the farms nearby. Suddenly, you're not allowed to do that anymore.
And you can monetize it. Not only do you can't throw it away that way, but you can actually get cash back by pelletizing.
To turn it into what has now become a huge cost. Am I right, Pablo, that now you're competing now against landfill, which is very expensive, whereas a few years ago you would have been competing against tipping it on the field nearby, which is relatively cheap?
Yeah. It's some years ago there was like some limitations to apply this technology. It is the inclusion of these fees for recycling boost the circular economy approach in our sector, at least. So for us, it helps. This the change of the situation helps, and also right now it helped a lot. The price of fertilizers is increasing so much from 1 year to now. It increased so much, and there's a lot of interest from all the agri sector in these approaches.
It's a little bit like the metals that you're extracting, Tim, and as much as buying them in is so very, very much more expensive, so it focuses the mind, I suspect. Any other questions? Well, yes, Tim, please.
Again, Pablo, I'm just thinking you're using this substrata as a base ingredient, right, for fertilizers. Can you then customize fertilizers to different products using your substrata as a base ingredient? It can be. We can blend another nutrients prior to pelletize the product, so it can be tailor made, or we can do a formulation on request from any crops. In fact, we have developed different fertilizers for cereal, vineyards, tomato, pepper. So we can add a lot of different nutrients just depending on the target crop. So this is a very advantage. This is a great advantage. Sounds like you're onto a winner there, mate.
It sounds good, doesn't it? Sounds like you're all onto winners. I'm impressed by all of you. Well, thank you very, very much for your time. It's been a pleasure listening to you and hearing about your work. Thank you.
Thank you very much, Abby.
Thank you so much.
Thanks very much.
Thank you, guys.
All the very best to you all. Thank you. Are you interested in what other EU-funded projects are doing to cut back waste and boost the circular economy? The CORDIS website will give you an insight into the results of projects funded by the Horizon 2020 programme that are working in this area. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from mollusks to meteors. There's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So, come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.